Okay, so we're doing this one now. All right. So this one is actually pretty interesting. Seems like a fun set of applied problems. We're going to try to, it's a pretty short section. We're probably just going to try to get to the exercises as quick as possible. But let's read through it because it does take a little bit. So, okay, so here's the model. Suppose a nation's economy is divided into n sectors that produce goods or services, and X is a production vector in Rn that lists the output of each sector for 1 year. So X is production vector in Rn lists the output of each sector for 1 year. Also, suppose another part of the economy does not produce goods or services but only consumes them, then D is a final demand vector. That lists the values of the goods and services demanded from various sectors by the non-productive part of the economy. What I like about this is that it really makes you think, because these real models, it's like you actually get to question them and be like, does this actually make any sense? So the vector D can represent consumer demand, government consumption, surplus, exports, other stuff. As the various sectors produce goods to meet consumer demand, the producers themselves create additional intermediate demand for goods they need as inputs for their own production. So what we can do is we can represent this as X, the total amount produced, is equal to the intermediate production plus D, the final demand. The interrelations between sectors are very complex. The basic assumption in the input-output model is that for each sector, there's a unit consumption vector in Rn that lists the inputs needed per unit of output for that sector. So that's like a one-hot vector, kind of. Well, sort of. Anyways, yeah, unit consumption vector makes sense. All input and output units are measured in millions of dollars rather than in tons of bushels or something like that. As a simple example, suppose the economy with 3 sectors: manufacturing, agriculture, and services. What a badass economy. Okay, so the column vectors, with unit consumption vectors C1, C2, and C3. Okay, what amounts will be consumed by the manufacturing sector if it decides to produce 100 units? So what it needs is, for 1 unit of manufacturing, which is like maybe $1 million of manufacturing output, it needs itself 0.5 or $500,000 in manufacturing input. Those diagonal entries are weird. There's agriculture to support agriculture. There's manufacturing to support manufacturing. And the input of services is more services. It's just kind of interesting. You would think that maybe those diagonal entries are 0 or something. But anyways, here's what I was saying. For 100 units of manufacturing, you need 50 units of manufacturing, 20 units of agriculture, and 10 units of service. An interesting question is how this matrix C, the consumption matrix, is actually determined. Okay, so the intermediate demand is equal to some production vector times this matrix. So the intermediate demand is equal to C times X, where C is the consumption matrix. Okay? So that's cool. So the total amount produced is equal to the intermediate production plus the total demand. You can rewrite this as I minus C times X is equal to D. Because the way this model sort of works is you sort of first you suppose that there is a given amount of demand for each of the sectors that is consumed non-productively. Then you figure out this consumption matrix, and you want to figure out basically what amount you need to make. So you're trying to sort of sync up with the rest of the economy, it seems like. So consider the economy whose consumption matrix is given by 3. Suppose the final demand is 50, 30, 20. So if D equals 50, 30, 20, then we want to solve for I minus C times X is equal to 50, 30, 20. So here we go, we calculate this. So now we want to figure out how much to make. And we end up, you solve the system and you end up with, you need this amount of manufacturing, agriculture, and services. All right, now this one I didn't understand. If the identity minus C is invertible, then we can apply theorem 5 and we can replace A with I minus C the theorem shows that in most practical cases, I minus C is invertible and the production vector X is economically feasible in the sense that it's non-negative. In the theorem, the column sum denotes the sum of the entries in a column of a matrix. Under ordinary circumstances, the column sums of a consumption matrix are less than 1 because a sector should require less than 1 unit's worth of inputs to produce 1 unit of output. I wonder if in the real economy, there are just drains that just it's like, why are we even doing this? Propped up by government or something. I don't know. Okay, theorem 11. Let C be the consumption matrix for an economy and D be the final demand. If C and D have non-negative entries, and if each column sum of C is less than 1, then I minus C inverse exists. Is that true? Wait, I don't know if that's true. What if you have linearly dependent columns? The following discussion will suggest why the theorem is true and will lead to a new way to compute I minus C inverse. Oh, you know why, though? Because even if C is linearly dependent, I minus C. What if C equals I? So C can't equal I because it's non-negative entries. And it has to be the sums have to be less than 1. Okay. Starting to see it. I don't know this treatment, though. Imagine that the demand D is presented to the various industries at the beginning of the year, and the what the hell? And the industries respond by setting their production levels at X equal to D. So if X equals to D, then X equals CX plus X. So then CX needs to equal 0. I don't know if that's actually true. It could also be that CX equals 0. Yeah, well, okay, I think CX would be have to equal 0. So as the industries prepare to produce D, they send out orders for the raw material. This creates an intermediate demand of CX, CD for inputs. To meet additional demand, the industries will need CCD. Of course, this creates a second round of intermediate demand, and you get C3D, and so it goes. Theoretically, this process will continue indefinitely, although in real life it would not take place in such rigid sequence of events. We can diagram the production level X that would meet all of this demand is oh, okay. Okay, this makes sense. Just take M to be like 2 or whatever. If you multiply these and you FOIL it, then you get I squared minus C squared. So M equals 1 in that case, I guess. Uh, CM approaches the zero matrix. So I minus the zero matrix is I. Okay, so then you end up with I minus C inverse is equal to the sum 0 to infinity, I guess, or whatever, of C to the M. I don't understand why we even need to compute this inverse. Why not just do LU factorization like we just did? The economic importance of entries in the inverse. The reason is they can be used to predict how production X will have to change when the final demand D changes. Okay. In fact, the entries in column J of I minus C inverse are the increased amounts the various sectors will have to produce in order to satisfy an increase of 1 unit in the final demand for output of sector J. That's cool. All right, practice problem. So there's two sectors, goods and services. So the consumption matrix is 1 unit of output from goods requires 0.2 units of goods and 0.5 units of services. On the other hand, services is 0.4 and 0.3. The final demand is 2030. Okay, so if we have I minus C times X equals D, we can shift over to this. And we're going to get, so we're going to get for this minus 0.8. Oh, wait. 0.2 minus 0.4 minus 0.5, 0.7. So this is I minus C times X is equal to 2030. So now, let's see, what did the problem say? It didn't say actually solve it. It just said set it up. But if we wanted to solve it, or rather we could do this. So now we want I minus C backslash D. Okay, so we need to make 72 units of goods and 94 units of services. All right, so let's look at some of these problems. Yeah, let's look at that. What did they say the inverse represents? Okay. Let's just start doing problems. We're doing an economy that's divided into three sectors, M, A, and S. For each unit of output, manufacturing... Okay, so let's just set up this matrix. So the consumption matrix is .1, 0.3, and 0.3. .6, 0.2, 0.1. 0.1 at the bottom, 0.6, 0. Okay, so let's just get so this is going to be number 1, so number 1, so 2.6, number 1. The consumption matrix I got was 0.1, 0.6, 0.6, 0.3, 0.2, 0, 0.3, 0.1, 0.1. Okay, now if we wanted 100 units of agriculture, so that's how much we need to produce to make that much agriculture. Okay, what's next? Determine the production levels needed to satisfy a final demand of 18 and nothing for anything else. So now if D is equal to, so for part B, D would be equal to 0, 18, 0. All right, so for part B, D is equal to 0, 18, 0. And what we want to do is I minus C backslash D. So that's how much we need. 33, 35, and 15. It says do not compute an inverse matrix. I did. Determine the production level needed to satisfy final demands for 18. Okay, so let's just do this, and this is going to be 18, 0, 0. 40, 15, 15. Determine the production levels needed to satisfy 18, 18, 0. All right, number 5. Consider the production model with two sectors. Um, Zero, 5, 6, 2. This is 5. 0 0.5. Oh wait, 0 0.5, 0.6, 0.2. and D is equal to, what did it say? 50, 30. And what we want is inverse of minus C times D. Okay, and let's just check that, oh my god, that's so annoying. Okay, then let's just double check that these are the same. Nice. Okay. No, we're not going to be doing that. Let's C and DB as an exercise 5, determine the satisfy. Okay, I'm not going to do that. This maybe I'll do 13. 13 seems pretty sick. Oh wait, hold on. Let's just read this. Okay, let C be an n by n consumption matrix whose column sums are less than 1, and X be the production vector that satisfies final demand D. Then let delta X be a production vector that satisfies a different final demand delta D. Show that if the final demand changes from D to D plus delta D, then the new production value must be X plus delta X. All right, so this is like challenging your understanding of linear algebra. Okay, I'll be right back though. Okay. So, um, so for this one, um, it's applying the linearity definition. So if we have two solutions to the Leontief input-output equation, we have I minus C, or let's just do this. So if we have, let's just say A is equal to I minus C, okay? If we have A x equals D, and we have A delta x equals delta D, we want to find A x plus delta x. This is going to be equal to, by linearity, A x plus A delta x, which is equal to D plus delta D. So this is just a direct application of linearity. So they just want to, reinforce that you're able to recognize when that shows up and how solutions can be whatever. So that's that. Okay, so part B says, let delta D be the vector in Rn with 1 as the first entry and zeros elsewhere. Explain why the corresponding production of delta X is the first column of the inverse. Well, if we have I minus C inverse times some D, and D happens to just be 1, 0, 0 or something like that, then A times 1, 0, 0 is going to be the first column of A. And since that's what that product is, then delta x has to be that. Just by the equation, delta, x equals I minus C inverse D. So since we have the first column of I minus C inverse, then that's what x has to be. This shows that the first column of I minus C inverse gives the amounts of the various sectors must produce to satisfy an increase of 1 unit. Okay, so that's cool. Number 9. Solve the Leontief production equation for an economy with 3 sectors. Bro, okay. Here, I'll do it just because I'm having fun. I can't be bothered to write all this stuff out. All right. So we have C and D, and literally it's just going to be I minus C, D. So this is how much they need to produce. This is what X is. All right, that was easy. The consumption matrix C for the U.S. economy in 1972 has the property that every entry is non-zero and positive. In the inverse, that means what does that mean? Raising the demand for just one sector that means that it's fully connected, I think is what that means. I'm going to ask ChatGPT, but I'm pretty sure that means that for any given sector, if you want to produce more of that sector, you're going to need more of every other sector, including itself. So let's just double check. Swagalicious. Yeah, exactly so. So, okay, so we were right. That's exactly right. Because the inverse tells you how much more you need. The production equation is usually accompanied by a price equation with the transpose of the consumption vector. Oh, that's cool. I'm not going to verify that, but that's obvious, right? Like if you have, you replace D with I minus C X. So then you have P times I minus C times X. Wait, actually, then V so in the price equation, V is equal to P minus C transpose P, which is equal to IP minus C transpose P, which is equal to I minus C transpose times P. So for V transpose, it's going to be equal to I minus C transpose times P transpose times P. Actually, if we just leave it as P transpose D, wait. Whatever. Let's do one of these cool ones. Let C be a consumption matrix. Yeah. Here we go. This one's cool. The consumption matrix for man, look how much of this is related to metal. It's crazy. It's just gonna be another backslash one. I don't really care. Wait, what is? I just want to know what the second to last one is. Services. Services is the biggest part of our economy. In 1958, it's closer to this. It became even more concentrated. It sounds like it's pretty nuts. What's the purpose behind learning this? I don't know, bro. I mean, if it can't get more applied than this, figuring out how much to produce for each sector to balance prices. I mean, I don't know how much more obvious of an application, it's just funny, dude. All right, but that's nice. This was a short section. So, we really probably only took me 38 minutes. This is a good one because we could just bang it out, not have to do much work. I don't know if I don't think I'm going to be doing 2.7, but I'll almost certainly be doing 2.8 and 2.9. That's subspaces of Rn and dimension and rank are like rank nullity. Rank nullity is probably defined in here. Theorem. The rank theorem. Yeah, there you go. There's that. Yeah, there you go. Rank nullity. They call it just a rank theorem. Yeah. I've never seen automatically used in a theorem before. It's kind of funny. Okay, the invertible matrix theorem gets more statements. A is n by n. Columns by a form of basis. Yeah, that's of Rn, true. And a basis is just defined as something that spans the codomain. I don't know what this means. Call of A. Do they define that? It must be defined in subspaces of Rn, but it's the column space. the dimension of the null space. I don't know why they don't use the word kernel. Everyone else uses the word kernel. So the dimension of the kernel is 0. And this is another way of just saying that the the null space. The null space is just the 0 vector. Okay. So next up is I don't know if I want to do this integrating factors section. We could always just spam linear algebra. So we could do this 2.8. It's wild that they define subspace before they define vector space. That's pretty crazy to me, actually. A subspace of Rn is any set H such that we have the 0, we have the sum of any, so closure under addition and closure under scalar multiplication. So that's all you need for subspaces. That's pretty chill. I guess you can define it. I mean, it's not like you really need to know what a vector space is to understand what a subspace is. We're going to go over all this in later anyways. Okay, the column space is the set of all linear combinations of the columns. Okay, that's fine. The null space is otherwise known as the kernel. Everywhere else calls it the kernel, so I feel like I want to call it the kernel. Plus, I sound cool when I say kernel. Maybe worth noting, but the 0, just 0 itself as a point, is a subspace. Okay, a basis for a subspace is a linearly independent set that spans the set. Okay, cool. Then they define the standard basis. The pivot columns of a matrix A form a basis. Yeah, that's chill. Okay, so this I don't think would be too hard. Let's see. Let A be this matrix and U be this. Is U in the null of space of A? So that means that if we did this matrix vector multiplication, I think it's not in the null. I don't know. I can't tell. It's got to be one or the other though. You can't simultaneously be. Wait, hold on. Can you be? Wait, hold on. Can you be in the null? So the null space is going to be defined as. So null of A is defined as the set of X such that AX equals 0. So for U to be in null of A, if and only if AU equals 0. Now, for A to be in call of A means the set of X such that AY equal X, pretty much. So I think actually you can be. I think a vector can be in the column space and the null space. Is that true? Okay, so U is in the column space of A if U equals AV for some V. And it's in the kernel if AU. Okay, that's cool, actually. That was a fun one. Maybe we'll do 2.8. 2.8 looks fun. It looks more theoretical. Yeah, so right. That's the better one. Is that 0 is always in call A and 0 in cur A. Cur and call. All right. So that's the Leontief input output model.